All right, welcome to our first recorded lecture here for Chapter 15 and Module 5 here for 1212. So what we're going to be moving into talking about is something called chemical equilibrium. We've introduced this term actually a little bit in the previous chapter with kinetics as we were talking about mechanisms and how the fact that when we had those mechanistic steps, if one of the early steps was fast, it would reach what we call this equilibrium. That's really kind of what we're going to be focusing on in this chapter, but we're going to kind of expand on it a lot. Because it turns out most chemical reactions will eventually reach that state of chemical equilibrium. And so we want to understand what that means, but also see what are all the applications that we can actually kind of use our knowledge about equilibrium for. So as a starting point, in terms of defining chemical equilibrium, there's a couple different ways to think about it. One is that equilibrium is the state where a reaction kind of reaches this point where all of its concentrations are constant. So your concentrations of your reactants and products aren't really changing anymore. But one of the most important things about this, though, is kind of a really easy misconception that I can see sometimes, is that this doesn't mean the reaction is over or that it stops entirely. What's actually happening is what we kind of described in the previous chapter, is that our rate of our chemical reaction in the forward direction becomes equal to the rate of the reverse reaction. And when that happens, we're now forming products at the same time we're using products and forming reactants at the same time we're using them. So the net result is all of these concentrations look constant, but in reality, our reaction is still taking place. And this will be kind of important as we get into something called the Chatelier's principle later on in the chapter. Not this lecture, but I think one of the following ones, in terms of trying to understand like why some of these different changes to equilibrium cause the different shifts that they do. And we can usually relate things back to kind of almost a rate perspective to be able to reason through a lot of those things. Now, visually, just to try and give some credence to what I'm saying, like equilibrium happens when our concentrations basically have this, pretty much fixed concentration to them. They're not changing anymore. And one of the neat things about equilibrium is the relative ratio of products and reactants. So in this case, we have the N2O4 reactant to make 2NO2. So actually, this would be our product and this would be our reactant in this case. It actually doesn't matter which, basically, one you start with. So for instance, in this example over here on the left, we actually start with just N2O4 at a concentration of about 0.04 molar. And over time, we see the concentrations kind of stabilize and we get concentrations of N2O4 and NO2. We can also do the same thing, but actually start with NO2, which is what happens here in the right diagram, where we have about 0.08 molar NO2. And when we get to equilibrium, we have pretty much the same concentrations of N2O4 and NO2 as we did if we started with just the N2O4. And so the equilibrium distribution, as far as like reactants and products, should pretty much always be reached regardless of which one you start with, which is kind of an interesting, neat thing about chemical equilibrium, is it really doesn't matter how you start out or where you are currently, like you're always trying to get to the same sort of equilibrium ratio of products and reactants. That's something we'll be examining a little bit more as we go. And to kind of show an example of rates, right? This is, in particular, if we look at this situation, starting with N2O4 and letting it decompose into NO2, here's a look at the actual rates of the formation of NO2, but also the backwards reaction to make N2O4, right? As our concentration of the N2O4 goes down, the rate of basically its consumption is going to start decreasing because it's kind of starting to level off. And what happens is the reason why then our concentration in the previous plot goes flat is that even if this rate is still here, like we're still using N2O4. But what's happening is the backwards reaction is now starting to take place as we have NO2 present. And eventually this backwards reaction starts happening at the same pace as the forward one. And the net result is now basically our rate of the consumption of N2O4 is the same as its rate of production by the reverse reaction. And that's what leads to that constant concentration over time once we reach kind of that equilibrium state. Now, I mentioned that there's this kind of fixed ratio of reactants and products that kind of always exist for a particular reaction. And this ratio, it's not quite so straightforward as, oh, you just divide like product concentration by reactant concentration. It's not quite that easy in terms of how things are related because stoichiometry actually also plays a role. And what we end up seeing is there is a constant ratio all the time. We see kind of this constant value here for this ratio that's given here for this particular reaction. And we have a whole bunch of experimental data that basically backs that up. And this expression for using the equilibrium concentrations is the same almost, for everything. To two significant digits, it's the same for pretty much all of them. But the third one's maybe a little bit of flexibility there. That's probably pretty standard when we're dealing with kind of small concentrations. So as we look at this, it's important to note that the NO2 concentration has to be squared for us to have this constant, basically, for the ratios. And if we think about it for a second, well, why does this have to be squared? Well, when we look at the balanced reaction, it does have a coefficient of 2. And that's what we're really going to see. All of our equilibrium constants, they are going to be relative ratios of products divided by reactants, but those products are always going to be raised to their coefficient's power, basically in the equilibrium constant expression itself. So the equilibrium constant, and do note this is a capital K. Remember I said before in previous lectures that lowercase k from chapter 14 was rate constants, capital K, or a lot of times you'll probably see K with either like an EQ or maybe a C or a P subscript for a lot of the parts that we'll see in this chapter to represent equilibrium constants. And in particular, KC and KP, probably the two more common ones. They're a little more specific. If you see KEQ, that's just kind of a generic equilibrium constant. But KC is basically just an equilibrium constant that's going to use concentrations to find it. KP then is just going to use partial pressures instead. And you can use either one, and their values might not be exactly identical all the time, although they are usually pretty close. But you pretty much just use whichever one's more convenient. If you have a gas and you have all the pressures measured, you can calculate KP. If you have solutions and it's easier to deal with everything in concentrations, you use KC. So you just kind of use whichever one is more appropriate for the situation, or whichever one you have the units for, basically, in the information in the problem. Now, in general, calculating the equilibrium constant Kc, and this is the one I'm going to start with because this is probably the more common one, especially once we get past chapter 15. Almost everything we do is a Kc. Kp is more common maybe in this chapter and kind of this chapter alone, but Kc will be a little more common than after that because most of what we'll do is kind of aqueous solution applications. Now, how we go about calculating the equilibrium constant, I mentioned it's still going to be this ratio of products divided by reactants, but we're going to multiply all the product concentrations times each other, but before we do, we raise each concentration to the coefficient power for that compound. So like little c is the coefficient of compound C, and so that we see compound C raised to that little c power. And we see that for our other products and for our reactants as well, kind of following that same trend. So products over reactants, it's all being multiplied, but those concentrations are raised to the coefficient power as we calculate things. So stoichiometry does matter for all of these things as we're putting everything together. And so that's why the ratio for Kc in that original example we had before, numerically, the thing that came out with that constant value all the time was that NO2 squared divided by N2O4 for the reaction of N2O4 making 2NO2. Well, again, the stoichiometry matters. This 2 here is because there was 2NO2 in the balanced reaction. And so that's kind of what we're paying attention to all the time in this. And so it's just products over reactants. Everything raised this coefficient power, so 2 in this case, 1 for the N2O4. All right, so a quick sample problem then. What can we do just at least initially with some of this information? Well, here we're given some equilibrium concentrations for a mixture that's at 500 Kelvin. We're told that N2 has a concentration of 3.0 to the minus 2, H2's concentration is 3.7 to the minus 2 molar, and ammonia's concentration is 1.6 to the minus 2 molar. And it asks us to calculate the equilibrium constant at 500 Kelvin for this reaction. Now, for equilibrium problems, if we're dealing with anything with equilibrium constants, the temperature itself doesn't show up in the calculation. The only thing the temperature is there for is just so that you're consistent with it all the way through. Because if we're not at 500 Kelvin, the equilibrium constant actually can change value. And so the fact that it's just saying all of this stuff is at 500 Kelvin is just letting you know there's no weird temperature effects on anything that we have to worry about. And in reality, in general chemistry, we pretty much don't even look at how temperature affects equilibrium constants, at least not from a calculation standpoint. There are ways to try and go and do that. We don't do any of those in this class. You don't have to worry about that. So temperatures typically in these equilibrium problems like this, not really going to play much of a role. The temperature itself probably isn't even going to show up in the calculation at all for anything that we're doing, unless maybe you're having to do some ideal gas law type calculation as part of the problem. Then maybe the temperature would get used. That's probably the only situation where that would really happen. Now, for setting up this problem, we want to find the equilibrium constant, right? So the easiest thing to do, if we're looking for the equilibrium constant and we're given like a lot of the information, is just look at our reaction and look, okay, in order to find the equilibrium constant, what do we need? We need to know the concentration of NH3, H2, and N2 specifically at equilibrium. And this will be the biggest detail that you'll see here for the first half of the chapter versus kind of the last part of the chapter that's actually on exam 3. It has to do with, are we given the equilibrium values or are we given initial values for things? And it sounds like a small difference, but it's actually, in terms of the amount of work involved, a huge difference between those two. For a problem like this one, where we're given the actual equilibrium concentrations, finding the equilibrium constant is actually quite easy. We can just write the equation for Kc, right? So I'll have the concentration of NH3 squared because there's 2 of them, divided by the concentration of H2 cubed because there's 3 of them, divided by the concentration of N2, to the first because there's just 1 of them. So putting in all of our numbers here, here's our concentration of ammonia, 1.6 to the minus 2. We have to square that. In the denominator, we have the concentration of H2, 3.7 to the minus 2, and we have to cube that portion because there's the 3H2 in the reaction. And then we have N2, 3.0 times 10 to the minus 7, or sorry, 10 to the minus second as well. And if we go ahead and calculate this out, we end up getting a equilibrium constant of about 1.7 times 10 to the second, or about 170. And so the next part of this is going to be talking a little bit about what do these equilibrium constants actually tell us, what do they mean. One of the first things we're going to note is actually that they have no units, which seems strange, right? We have basically like a molarity squared divided by molarity times molarity cubed, but yet we have no units at the end. So where does that come from? So I'm going to kind of just mention this briefly. It's not something I'm really going to test you over, but all equilibrium constants are always going to be unitless. Like that part you should know. The reasoning for that is that we always compare either concentrations that we're using, or if we're finding Kp, the pressures that we're using, to what we call standard values. And for something to be at standard conditions from 1211, and we'll review it a little bit later on in 1212 here as well, but standard conditions usually means like 1 atmosphere of pressure, 1 molar for a concentration of a solution. And we don't have to necessarily be at those conditions for our problems, but effectively what we're going to do is get ratios compared to standard conditions. So if we're putting in concentrations here, like this 1.6 times 10 to the minus 2 molar, we're effectively dividing it by 1 molar, which would be the concentration of a standard solution. So the number doesn't change, but the units do go away, and that's how we end up with this unitless equilibrium constant at the end. So it's a little strange, but probably the easy thing to recognize just here is that equilibrium constants do not have units. They're pretty much the only thing we see all semester almost that don't have units that we have to worry about. All right. Now, in terms of how does the equilibrium constant affected by the ways we write our equation? It is going to be pretty important, right? Balancing things is going to matter because coefficients show up in our calculation of the equilibrium constant. So when we have a reaction like this top one and we reverse it, back in like 1211, we looked at things like what happened to enthalpy when we reversed reactions or multiplied by constants. We're kind of having a similar look here for equilibrium constants because it's a little bit different. Instead of like for delta H, where if you reverse a reaction, you change the sign, the equilibrium constant actually becomes inverted, right? Because equilibrium constants are products over reactants, while reversing a reaction switches what our reactants and products are. And so now instead of being negative, it inverts, right? So our new equilibrium constant here would be 1 over the original one. If we multiply things by a constant, remember what happens. These coefficients in our problem or in our balanced reaction always show up as powers of 10. So if I multiplied everything through in a reaction by 2, I'm actually effectively squaring everything in this particular reaction. That's the net effect, right? Because instead of having NH3 squared, like I had originally, and then like N2 and H2 to the third, I'm basically multiplying all those exponents by 2. And so I'm effectively squaring the equilibrium constant compared to what it was before. If you were to multiply through by a constant of 4, you'd be raising everything to the 4th power, or that equilibrium constant to the 4th power, in terms of the changes that are then occurring. Now, I also want to talk briefly about kind of the other version of the equilibrium constant we do see in this chapter, Kp. The only real difference is Kp uses pressures as opposed to concentrations like Kc, but the two are very closely related. but it's important to note they're not always the same value. And so if there is ever a case, and this is something that like I probably would never test over just because I don't think it isn't practically useful most of the time. Like if it's easier to calculate KC, you usually just calculate KC and use it. If it's easier to calculate KP, you usually calculate KP and use it. Very rarely do you have to go back and forth between the two. But if you do, this is an equation that can help you do that. Where Kp is equal to Kc times this RT to the delta N power, where R is just our ideal gas constant. It is the one that has liters and atmospheres for units again, because we are like getting this equilibrium constant that's going to really deal with kind of relating pressures and things like that as well. T involved here does have to be in Kelvin. Again, anytime we use temperature, it needs to be Kelvin. And then delta N is maybe the weirdest part here. It's the change in moles of gas. So it's basically the moles of gaseous products minus the moles of gaseous reactants. So for instance, in this equation over here, we have N2O4 going to 2NO2. Here we have 2 moles of gas, then minus 1 mole of gas would be a positive 1 change in the moles. So delta N would be plus 1 for this example. So that's what that delta N is in that equation, and why there's a delta there with the number of moles. Now, as we go through and write equilibrium constant expressions, there are a couple kind of quirky things a little bit in terms of things we have to kind of keep an eye on. And in particular, you'll hear people talk about homogeneous or homogeneous equilibrium versus heterogeneous. So most of what we look at in this class is going to be homogeneous or homogeneous equilibria with an occasional solid maybe mixed in which might make my particular example heterogeneous instead. But the reason we care about this is that solids and pure liquids actually don't really affect equilibrium or its calculations, which should hopefully make sense, because if you have a solid in your reaction, how do you measure the concentration or the pressure of a solid? I mean, you really can't, right? So what ends up happening is anytime you would have like a solid or a pure liquid in an actual equilibrium constant calculation, instead of putting the concentration and the pressure of the solid, you actually just put 1 as kind of like a placeholder. And that actually then allows the math to work, and we can actually still see the same ratios we expect to see in comparison to normal. And one of the neat things about this, though, is that if you have an equilibrium that involves a solid, you can add more of that solid at any point in time, and it shouldn't do anything to the equilibrium. It's not going to change it, which is also kind of a bit of a weird, unique feature that kind of comes out of this. So to kind of show an example, if we have the reaction of calcium carbonate as a solid, decomposing into calcium oxide as a solid and carbon dioxide as a gas, if I want to write the equilibrium constant expression, normally I would write it like this, right? Products over reactants. But since the calcium oxide and the calcium carbonate are both solids, at the end of this, my equilibrium constant is actually just the concentration of CO2. That's the only thing that's left because these are both 1. And so that's kind of a neat thing that happens when we do have solids. This also applies to pure liquids, although those are much less common in these kinds of problems. Solids, on the other hand, show up fairly frequently for these potential types of problems. And what this image is basically just showing then is if our equilibrium constant equals the pressure of CO2, that means if we can measure the pressure of CO2 in a container, we immediately know the equilibrium constant, which can be useful if we change some of these conditions, particularly temperature usually being a really common one, because as you change temperature, usually that equilibrium constant will also change, All right, now, numerically, what does this equilibrium constant actually mean? And what kind of values do we expect? Well, in terms of the range of values for equilibrium constants, they can range from really, really small, like here we see an example of a reaction with 10 to the minus 48 for its equilibrium constant, compared to really, really huge. So here we have like 2.4 times 10 to the 47th for an equilibrium constant. So equilibrium constants, huge range of numerical values that are possible. But in terms of what they tell us, pretty much anything close to 1, within like even a couple powers of 10 of 1, so like, maybe from like 0.01 to like 100, something like that, pretty much our amount of products and reactants aren't that much different. There's going to be a little bit of difference. If our equilibrium constant is bigger than 1, that means we do slightly favor our products. If it's smaller than 1, we do slightly favor our reactants. But in kind of this intermediate range here in the middle, there's not much of a difference in terms of how much of the reactants and products we actually get. They're going to be similar amounts of each at equilibrium. Now, if we have something where our equilibrium constant is really, really big, so we're over here, like, in kind of the red part of this arrow, kind of like this example, times 10 to the 47th power. At that point, that power is so big, there pretty much isn't any reactant left, right? We've effectively gone to completion at that point. And not many reactions actually do that. There's only a couple that we normally know offhand that go to completion. Most precipitation reactions will do that, but not all. A lot of the ones we saw in 1211 do kind of do that. But probably the best example is usually combustion reactions. So combustion reactions usually go pretty close to 100% completion in terms of how much reactant versus product is usually left. So usually combustion reaction, if it's almost all products, it has a huge equilibrium constant as a result. Now, the last part that I'm going to introduce kind of here at the start of the chapter, and then I'm going to kind of end this first recorded lecture, and then I'll have a little bit later, probably sometime tonight or tomorrow, you'll see some practice problems on this, as well as kind of the next portion of chapter 15 that will be on this week's exam, which is Le Chatelier's principle. Will be kind of the only probably new additional piece that will really add. So not really a whole lot more of chapter 15 coming for this exam. The big bulk of the calculation side will actually probably be after. Which will hopefully make things a little bit easier as we get ready for this next exam. But this reaction quotient will be on this week's exam, and what this reaction quotient Q is it's a way for us to examine reactions that aren't at equilibrium, right? We said before that for us to find the equilibrium constant, those equations and expressions that we were showing, your equilibrium, all those values, like your concentrations and pressures, have to be at equilibrium already to be able to use to find the equilibrium constant. And then the numbers of like the numerical values of K gave us information. If it's a lot bigger than 1, it favors products. A lot smaller than 1 favors reactants. Somewhere in the general vicinity of 1, basically within an order of magnitude or so, tends to favor really neither. You get pretty similar amounts of each. And what the reaction quotient is, you basically calculate it the exact same way you would the equilibrium constant. You just use whatever your current conditions are. You don't have to be at equilibrium anymore. It just kind of removes that stipulation. And it's actually kind of useful from an experimental standpoint because if you can calculate Q, you can compare that to the equilibrium constant to figure out, is a reaction at equilibrium? Does it have to go farther in the forward direction to get to equilibrium, or is it actually going to go in reverse to reach an equilibrium state? And so how this happens is we actually just compare the values of Q and K. In the situation where Q and K are equal to each other, that would mean that our reaction is currently at equilibrium. If we calculate our reaction quotient and it's much less than the equilibrium constant, or just smaller than the equilibrium constant in any capacity, that means our reaction has to go in the forward direction. Basically means that since equilibrium constants are products over reactants, if Q is too small, we don't have enough products yet, so we want to make more products. That means the reaction will go forward. Now, the opposite's then also true. If Q, our reaction quotient, is bigger than the equilibrium constant, effectively means we have too many products. So we're going to use those extra products that we aren't supposed to have to make more reactants, and so our reaction is effectively going backwards at that point. And so that's kind of the check that we're usually looking to try and make with our reaction quotient. A lot of times, like example problems for this will be just like looking like, here's our current conditions, here's the equilibrium constant, which way will the reaction go? So let's take a look at an example of doing just that. So here we're asked to consider the following reaction. We have 2NO plus Br2 making 2NOBr. We're told the equilibrium constant is 116.6. And we want to know what direction will the reaction proceed if the current pressures are 1.05 atmospheres of NO, 0.400 atmospheres of Br2, and 0.969 atmospheres of the NOBr. So I'm going to show this in the slides on this one because, like I said, I'm going to have kind of a whole different lecture with some additional examples, walking through like kind of things that we can expect to see or try to answer with a lot of this information. But I'll have that as a separate lecture just from kind of a time standpoint so that this one doesn't get too exorbitantly long. But set up for this, to find Q, I'm going to find it the same way I would the equilibrium constant, which is going to be my products raised to their coefficients power, divided by my reactants raised to their coefficients power. And it looks like there's actually a small typo here. This should say squared right here. And actually, let me check the math to see if that number actually is properly being squared. I apologize for the typo here as I'm looking right at it now and seeing it. All right, so it actually looks like this number is off just a tiny bit. This number right here should be being squared, and this number actually should be, I believe, 213 roughly, is what it comes out to instead, which actually doesn't really change much as far as what's going to happen with the reaction. But I really want to make sure that and kind of emphasize that. I don't know if it'll actually let me adjust this. Yeah, I don't think it's going to let me adjust this, unfortunately, right now. So I apologize for that. This is our last slide, actually, anyway. But this should be 0.969 squared divided by 0.105 squared times zero point 0.4. If you calculate that out, it's going to be pretty close to this. Instead of 220, it's about 213. And if the equilibrium constant is 116, the big thing, the important part of all this, Q is still bigger than K. And if Q is bigger than K, that means we already have more products than what we're supposed to, which means the reaction will go backwards towards reactants in order to get to basically that equilibrium state that all reactions try to get to. And that's kind of our main application of Q is we're going to calculate the same way we would the equilibrium constant. Be very careful. Make sure you include those coefficients as your exponents, unlike I kind of did here for one of ours, unfortunately. And then compare your reaction quotient Q to the equilibrium constant to figure out, all right, which way are we going to reach equilibrium? And in this case, we had too many products because Q was too big, so we got to go backwards. That's kind of the main application of this, and I will have a couple more examples of this in kind of the next little example video that I put up, and I'll be certain not to have any more coefficient errors here. I'll walk through them on my whiteboard as opposed to walking through them on the slides here, so that hopefully that will help with that process. But that hopefully gives us kind of a pretty quick introduction here to a lot of the stuff that we'll see here in chapter 15 and really kind of beyond. We'll see this applied to a lot of different things. The rest of chapter 15 that we'll actually have for this week's exam will actually probably just be Le Chatelier's principle, which isn't really calculation based, it's much more conceptual. And so we'll see a bunch of examples of that in the next recorded lecture. And then the last part of chapter 15 after this week's exam, we'll be taking a look at what big calculations can we start doing with equilibrium constants, because there's actually a ton of applications of using them to be able to do calculations and understand reactions better. In particular, we'll be looking at like if we have starting amounts of all of our reactants and products, how much product do we end up with at the end when we get to equilibrium? That becomes kind of the next step of things. And that's actually a much harder calculation than just finding like an equilibrium constant if we have all the equilibrium information to start with. So that'll be kind of our next thing that we'll move towards. But that's all I have for this time. Kind of keep an eye out for some more examples for things like reaction quotient and just equilibrium constants in general here that I'll post up probably in the next day. And then, like I said, I'll have the Le Chatelier's principle up probably shortly as well. And then we'll have ice tables and things like that that'll come up. You'll probably see them before our exam 2 as far as being posted, but that content will not be on exam 2. And I'll try to make sure I reiterate that fact kind of constantly in these lectures and by email and stuff just so that everyone knows exactly what you're looking at for your exam 2 content.